Compound A is a halogenoalkane, so it's got a Cl group, it's got 5 carbons in a line, it's got 2 methyl groups, so it's pentane because it's got single bonds, 5 in a line. It's symmetrical, so it doesn't really matter whether we start labeling from the left or the right, we're going to end up with the same numbers for the methyl groups and the Cl, so it's 3-chloro, 2,4-dimethyl pentane. 3-chloro, carbon number 3, 2,4, number 2 and number 4, di-2-methyl groups pentane. It's important that you have the C for the chloro alphabetically before the M for the methyl. Let's have a look at this then now. Compound A has relative molecular mass of 134.5. The main isotope is hydrogen mass 1 and carbon mass 2. Chlorine consists of 2 common isotopes, 35Cl and 37Cl, of which 75% is 35Cl, so 3/4 of it, 3 parts out of 4, are 35Cl, 25% is therefore 37Cl. So this is 3 times more common. 35Cl is 3 times more common than 37Cl. The mass spectrum of A was recorded when A was ionized. So what actually happens is you have something called an electron gun. An electron gun removes an electron from this and makes it plus charge. Doesn't really change the mass because an electron has got negligible mass. So removing an electron doesn't really change its mass, but it makes it plus charge so that it can be accelerated down the mass spectrometer tube and then detected at the end. So basically it's saying that there are peaks for the molecular ions in the mass spectrum of A. What will they be? Well, if that's, you need to work out the MR. The MR with 35Cl I think will come out as 134, and with a 37Cl it'll come out as 136. So you're going to end up with peaks at 134 and 136. The one at 134 that's got the 35Cl, which is 3 times more common, will have a higher peak because relative abundance means how much of it there is. So if we had 1, 2, 3 lots, parts, amounts, whatever you want to call it, at 134, that would compare to 1 part at 136. A reaction with warm dilute aqueous sodium hydroxide. So if we're using dilute aqueous sodium hydroxide, then aqueous means water, so water, sodium hydroxide in water, what actually happens is you get nucleophilic substitution. So the mechanism is that this C to Cl bond is polar, so that's slightly electronegative. The Cl is electronegative, gets a slight delta minus charge, slight delta plus charge, and the OH minus bonds with or attacks the C, because that's got a slight delta plus charge, and the Cl, which is withdrawing electrons because it's electronegative towards itself anyway, gets the electrons and forms a Cl minus ion. The Cl minus ion is missed off from this side, but it forms Cl minus. It's a minus because electrons are moved onto it, and the OH bonds where the Cl was. It can either be up or down, it doesn't really matter. In this case it's drawn going upwards. Important that you have OH minus and that you don't include the Na. The Na, the sodium, is a spectator ion. You only use the hydroxide part, which is OH minus, and it's important you show the lone pair because it's the lone pair that bonds to the C. That lone pair forms the share with a dative or a coordinate bond, a covalent bond between the O and the C. With hot ethanolic potassium hydroxide, so with hot, ethanolic means there's ethanol present. This time you don't get nucleophilic substitution. The OH minus doesn't attack that C. What it attacks is, if you go find the C with the Cl, there it is, there's the C with the Cl, and you go along another C. Either way, it doesn't matter in this case because it's completely symmetrical. You go along another C, from the C with the Cl, you go along another C, and you identify hydrogen bonded to that C, which is that hydrogen there. It's that one that it attacks. So the OH minus attacks that hydrogen there. So again, you identify it C to Cl, you find that carbon, you go along another carbon, either left or right, doesn't really matter in this case because it's symmetrical. Find the carbon, let's say to the left, and find the hydrogen bonded to that carbon. The OH minus bonds with it, and it actually make water. HHO. So the H2O loses its minus charge because electrons are moving away from it, and it will make H2O. This bond then breaks and it moves in between the two carbons here, between the carbon that the H has been bonded to and the carbon with the Cl, and forms a double bond here, and then the Cl breaks off. So just like before in nucleophilic substitution, the Cl bond breaks off and it'll make Cl minus as the electrons move onto the Cl. Mechanism, elimination. The reason it's elimination is because atoms have been removed from this. One product actually makes three products, Cl minus H2O, and this, which is got a double bond, an unsaturated hydrocarbon here. So atoms have been removed, eliminated, elimination. And the role of the hydroxide ions is the OH minus has gained an H plus to become water. So it's gained an H plus, something that gains an H plus. Remember, an H plus is an acid, and something that reacts with an acid is called a base. The infrared spectrum in figure 4 is that of either alcohol B or alkene. So we're looking for either an alcohol, an OH, or a double bond C. Which one is it? Well, it's easy to identify that actually it's not the alcohol. That's the easiest way of doing it, because an alcohol has a very, very broad absorption peak here. A really, really wide, deep absorption peak here. Not sharp like this, it's really, really wide. In an OH, either an OH of an alcohol or an OH of a carboxylic acid. The OH of the alcohol are both wide and broad. It's around about here, 3000 to 3500. It's around about here, 2500, 3000 for the OH in a carboxylic acid. But in either way, as long as you've got an OH in an alcohol or a carboxylic acid, you end up with a really wide, broad peak here, and it's absent. So it's not alcohol, it's an alkene. A carbon-to-carbon double bond is actually that one there, around about 1600, 1700, something like that. It's not very big, it's hard to identify, and that's why it's easy to identify that it's not the alcohol, because it's not got the OH broad absorption at around about 3000 to 3500. Explanation. The carbon-to-carbon double bond, you must quote these numbers from your data book, 1620 to 1680. Remember, we're going right to left for our scale, so it is that one. So that one identifies the carbon-to-carbon double bond, or as I said, no OH at around about 3230 to 3550. Nothing here for an alcohol. Quote those numbers from your data book, you don't need to remember them. Compound D reacts with aqueous sodium hydroxide in a similar way to A to form alcohol B. Explain why D reacts more quickly than A with aqueous sodium hydroxide. Remember, dilute aqueous sodium hydroxide with water is nucleophilic substitution. So the OH minus is going to bond with, attack this carbon here or this carbon here, and the Cl breaks off, that bond breaks, and electrons move on to the Cl and make Cl minus. Or in this case, D, the only difference is instead of a Cl, you've got a Br breaking off, and it will form Br minus. Why D would react more quickly than A? It's simply because this bond between the C and the Br breaks more easily. It's weaker. So you can say the C to Cl here is stronger than the CBr, or the CBr is weaker than the C to Cl bond.